Okay, hello. So what we're going to try to do this time around is write ourselves a very basic explicit list-based allocator. And I'm going to attempt to do this. You may have to suffer through some debugging, but I think that's the point here. We're not going to try to do anything fancy, but we'll see if we can get it to work, do a little bit better than the naive allocator, and hopefully along the way you'll see how to create the structures used in defining an explicit list and how to navigate them. All right. So currently, do a make, I've already made it, and as you know, we can do a -v. Right now we fail with just about half of the trace files that we run it with, and of course we can test the thing with short trace files, and we're not really going to try and do any better than this in terms of throughput, because you can't really beat the naive allocator in terms of throughput. But at least in terms of utilization, in terms of not always chewing up more heap space, we'll do a little bit better than this. And it's also going to beat the implicit list allocator from the book, if that's what you're starting out with. All right, so let's get started. So I've got the naive allocator here. Let's delete the comments. Not going to be that naive anymore. And the first thing we're going to want to do is we're probably going to want to define the structures for the explicit list. And let me go ahead and start doing this. So let's call this a header. And now we're going to want some size. And so we've got our header structure defined. And you know what? I'm going to also define a type def, because I don't want to keep typing struct header all the time. And I can go ahead and simplify these a little bit. Okay, so I've got my headers defined, and notice that I have a doubly linked list. And you know what I'm going to do in my init, remember this gets called the first time before our Alex or freeze ever get called, so the memory library makes sure it calls our init. I'm going to go ahead and create one of these things on the heap. And my thought process right now, I may have this wrong, but I'm going to always want my linked list to be around. At least I'm always going to want it to have a head element. And so I'm going to go ahead and create one. So block header, and remember I can't use malloc obviously to allocate one. So in order to create one of these things, I'm going to have to call membsbreak. And I'm going to want my header size, and I'm going to get tired real quick of typing in the header size, so I'm going to define a block header size. Let's use a line, and let's do size of block header, and that's going to have to come, oh, that'll be all right. All right there. Okay, so block header size is what I want. And let's see, for now, let's make it point to itself. And I'm not sure what to do about the size just yet. I can make it have its own size, I suppose, but you know what, let's worry about that later. Okay. So as always, I recommend that you constantly compile your code over and over again. The thing compiles right now, so I'm not going to worry about it. And we'll continue. So currently in the naive allocator, we can see that it's always calling membsbreak at the second line here. Now this part's not so bad, where we compute a new size. Now it's not sufficient anymore, because currently it's creating a size plus size t size. Now we have a block header that contains the size. So instead of size t size, what I really need is I need to allocate a block header size plus the size, and that's how much space I need for a new block that I allocate. Now, like I said, I'm not going to try and get too fancy here. I'm just going to always have a block header for every block, whether it's allocated or free. As you're working in your lab, you probably want to think about eliminating the header and just saving a header word for for your allocated blocks. Again, I'm just going to make this as quick as possible and as easy as possible. So I have my line here, and I'm not always going to call mem_sbreak, so in fact I'm going to want to allocate memory some other way here. And the strategy that I advise in class is to implement some sort of a find fit method. So I'm going to want to call some find fit with a new size. And let's go ahead and write our find fit here, and it's going to need to return a void pointer. It's going to take a size t size for that. And let's go ahead and define the prototype up at the top. You can define it after all this. So void find fit. All right. So we're all good. And at this point, we have to think a little bit about how to create this new block. Now, in point of fact, I'm going to want to return a block pointer. I don't have to change the prototype there, but I can change it here. So I actually want a block header. And let's go ahead and create a block header here. Pointer. So let's see. So we assume for now that my find fit is going to use my explicit list. And let's assume we have an explicit list sitting around. And like I said, my thought process, we'll find out if it works eventually. If not, we'll have some fun debugging to do. But my thought process is going to be that as we navigate through this explicit list, we always want to make sure to have at least one free block. And I think what that's going to allow us to do is basically have a circular linked list for free. If we never eliminate the last block, then obviously if the last block points to itself forward and backwards, we'll always have basically a single block circular list. So let us assume that we always have a start block. And I'm going to go ahead and use a for loop and see if this works. And the first block on the heap is always going to be my first start block. I know that because in mem_init I get my first free block essentially here by calling mem_sbreak, and that call to mem_sbreak is going to return the essentially it's always going to return memheap memheap low, and since that gets me back my first block on the heap, we'll assume that's the first free block, and that free block always remains my linked list, and so I'm going to go ahead and get that guy's next. Okay. Now I'm going to want to iterate as long as I don't fall off my list. In this case, let's see, we've gone to the next block first, and so not falling off my list means not going back to the beginning. So in this case, and excuse me for not writing particularly optimized code, but that'll make sure I don't fall off the list. And as long as I don't find something whose size is greater than or equal to the size, I want to keep iterating. So as long as the size of the block I'm looking at is less than the requested size here, I'm going to keep iterating. Otherwise, I go on to my next block. When I get out of this loop, as long as I found something that isn't the first block, then I'm going to return it. Otherwise, we return null. Okay, I think that just might work. Now we still have to think about what to put inside my, whoops, sorry, the first block I create here as far as its size. Haven't forgot about that. And you know, it will be tricky this time around because I'm not doing anything fancy. I'm just going to store 1 in there just to make sure it never actually gets looked at. And I think that'll be okay because we're never really going to, I'm not going to think about coalescing just yet. Eventually, if I think about coalescing, I'm going to have to worry about footers. Right now, again, we're not coalescing. We don't really need footers, so I'm going to ignore that, and we'll see how far I can get with that. Okay, so we have ourselves a find fit, and at this point, part of this code will probably still work. Now remember that if find fit, let's actually change this to block pointer. So a block pointer at this point is null. Then remember what that means is I didn't find anything in my list. Right? So what that means is this is going to have to call sbreak, in this case with, looks like new size is the size I need to call sbreak with. All right? And we can still keep this code here, at least portion of it. So I'm going to put that there. And the only difference being if it returns, see a -1, that means we had no space. Otherwise, I think there's a little bit more that we have to worry about here. This certainly isn't going to work, so I'm going to get rid of that. We'll think about it a little bit more. So if, however, it does return null, let's work in the else first. Oops, it's not going to be happy with this. And that's good now. Okay. So we're in the else part of this block, and if BP is not null, that means we're able to find a fit in our current in our free list. And if we find a fit, then the first thing we're going to want to do is make sure that we mark it as allocated, right? And then we're going to want to, since we return a block directly without removing it yet, the next thing we're going to want to do is remove it from the list. And for this, let's see, we want the prior guys next to be equal to my next, and we want my next prior to be equal to my prior. Okay? And that is, hopefully everyone recognizes, just a basic linked list removal. Okay. Now as far as this portion up here, if sbreak returns null, that means that, or if sbreak returns a negative value, that means that I'm going to simply return null. You can't find anything. Otherwise, let's think about what that means. So I now have a block pointer to a brand new block of memory that has nothing in it, and we're going to be allocating this block of memory. So I'm going to want to initialize this block's size to new size, and at the same time I'm also going to want to set it to allocated. Now I don't need to initialize its prior or nexts. Remember, they stick around anyway because I've allocated enough room for it because I allocate a block header size. But note that I don't actually need to do anything with them because they're not going to my free list. So I think that's going to work. And let's see, what do I want to return? Well, I don't want to return the block pointer. Remember, I want to return a pointer to the payload. So I'm going to return BP plus block header size. Now that's not going to work immediately or directly because BP is a block header pointer, as you can see up here. And I actually want to make sure I'm doing byte-based arithmetic, so I'm going to have to cast that to a character pointer. Okay, so I think we kind of have malloc here ironed out. Let's move on and see what else we have to do. So free's not doing anything. Obviously, that's going to be okay. Realloc is basing a size on some size t size based thing I'm storing beforehand. That's certainly not going to work, so I'm going to ignore this. That's not going to work. And for now, let's just return null, because the first few trace files don't actually use realloc anyway. If free doesn't do anything and malloc does its job, this isn't exactly going to prove anything, but let's compile this. And whoops, got ourselves an error. So line 52. Whoops. I'm not used to working in the terminal version of Emacs here. Alright, so 52. Oh. We are BP now instead of P. And very good. No errors. So I'm going to go ahead and switch back to my shell here. And let's try to do an M driver with the same short trace file. Okay. So now notice we ruined our utilization here a little bit because we've got some more block overhead, but things are still working. That doesn't prove anything, of course, because currently all we're doing is we're mallocing and we're not freeing anything, so we're actually not using our free list for anything whatsoever. But that's all right. We made sure that something worked. Okay, so let's see, before we go on, an interesting thing to be able to do would be to, and this is something that the write-up advises I think that you do, would be to iterate through our list. That is, the implicit list that forms our heap at this point. And note that, I mean, even though we're creating an explicit list here, because of the assumption that every block contains a block header, we can actually use that information as an implicit list. Because if you look at this header description, the size is always the first thing in the block. And we can use that to iterate through the list. So I'm going to go ahead and define, let's just call it, let's make this really simple. Let's call it print list. How about print heap? And let's not worry about any arguments right now. I'll put that right underneath meminit here. And okay. So what we're going to want to do is iterate through the entire heap. And let's see, let's think about how to do this. So we'll assume that we have a block header, BP, and we're going to set that at mem heap low to begin with. And that's okay, because mem heap low is, again, it's always going to be valid, because the first thing we do in meminit is to create this block here that, whoops, this isn't going to work anymore, because I'm going to want size to be correct. But you know, we can fix that to the size of the first guy is in flag. See, and you would fix that sooner or later, the block header size. And that's probably going to be okay, because I'm never going to look for a block that is precisely the block header size anyway, because malloc will always request at least 1 byte. All right, and we can fix that later if we need to. We'll see if any of the trace files break that. But all right, so we have a block pointer to the first block, and now I'm going to want to use the size of each block to navigate through the heap and print things out. Okay, so let's see, how shall we do this? So we want to iterate while, let's say while BP is less than mem heap high, and I want to, let's see, we'll have ourselves a fun printf statement, and let's see we want to figure out whether we have a free or empty block. We want to print out you'll see where I'm going with this. So a block at, we want a pointer, size, and we'll print out some size, and let's just make that an integer. We'll assume it'll fit. Okay, so time to fill out these things. So for set s, we want either allocated or free, and we're going to base that on whether or not, let's see, BP's size ended with 1 is true or not. And we've used this conditional elsewhere this semester, but it's an extremely useful type of expression. In this case, it's saying if the size ended with 1 returns true, returns 1, then that means the block is allocated. So we're going to map allocated, or have allocated, be printed out for this format placeholder, and free otherwise. Okay. And as for the pointer, that's simple. That's just BP. And as for size, we're going to want to, let's see, we're going to want to cast BP size into an int. Okay, and when we're done with that, we want BP, we can't use BP next P, because that only goes through the explicitly linked free blocks. Instead, we're going to want to move BP along. So let's see, we need to eventually pass this node block header. But we're going to want to deal with BP as a character pointer, and we want to add BP's size but we want to make sure that we end that with a complement of 1 so that we get the size without the allocated bit. Right? All right, let's save that. Let's see if that weird little expression there compiles. And let's see, sure enough, it does not. Line 45, which is right here. We're comparing different pointer casts. That one's easy. We just cast this one to a block header pointer, and we should be golden. Okay, we're good. All right, so let's go ahead and test this out. And the way we're going to do this, I'm going to go ahead and GDB this, and set a breakpoint at malloc, and for good measure at free. Although currently that doesn't make a difference, but that's all right. In fact, let's do one in init too. And let's go ahead and run this with the trace file short 1. Okay, so we're now inside init. Right? So I'll step through init, and let's verify that we're in init. Yeah, we are. So step, 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 and in fact, let me hit continue. We're now in malloc, and I'm going to go ahead and call, and if you didn't know you could do this, this is extremely useful. I'm going to call print heap, and there we go. So notice that it prints out that there is a free block currently of size 24, 24 because presumably the, let's actually try and make sense of that. So if we take a look at our header structure, I have 1, 2, 3 words, presumably each 8 bytes large. Our alignment is 8, recall, right? That's 8 right up here. And 3 times 8, sure enough, is 24. And that's the size of our free block, okay? Which is basically a standalone header. Okay, so where are we now? We're currently in, I think, malloc. So I'm going to go ahead and, yeah, we are in malloc because we see malloc got called with 2040. I'm going to hit continue to step to the next malloc, and I'm going to call print heap again. And this is kind of fun. All right, notice we have an allocated block at some address with size 2065. 2065 is because we failed to get rid of the allocated bit in the size here. And you know what? While we're at it, why don't we fix it? So for size, we're going to take size, and we're going to end it with the complement of 1, which we should have done earlier, but I forgot to. Let's compile that again. It compiles just fine. And let's switch over to GDB again, and let's run it again. Now, when I run it, it's going to load the new binary, or at least it should. Okay, did it? Yes, it did. You see it says mDriver has changed, and it's going to reread the symbols. So I'm going to hit continue again, continue again, continue again, and let's go ahead and call print heap again, and notice, there we go, we fixed our sizes. Pretty neat. If I hit continue again, we were just in free, and nothing got freed, because unfortunately we haven't fixed free yet. So that's the next thing we're going to want to do. Okay, so let's go back here. In fact, let's quit out of the debugger. Okay, so let's start working on free. So let's see. The first thing we'll want to do, we have a pointer to the payload. All right, so the first thing we're going to want to do is get ourselves a block pointer, and we can do that by pointer, and we want to go back precisely the size of the header, right? Right. And let's see, we're going to want to free it up, okay, which is just ending it with a complement of 1. We already know how to do that, right? And the next thing we're going to want to do is take the block, which we just freed, and now we have a free block that we can shove back onto the explicit list. Now keep in mind, we're not doing coalescing. If we were doing coalescing, we would need to, at this point, check the prior block and the next block to see if they're free. We can't even check the prior block at this point because we don't have a header, or excuse me, we don't have a footer. Okay, so that's something you're going to have to implement on your own. So I also need a pointer to the header, so let me put that in there. So this would be the head of the free list here, and I'm going to call mem heap low for that. Okay. And good old linked list manipulations. So I'm going to start out by making my next equal to the head's next. Okay, I'm going to make my prior equal to the head. Okay, and then I'm going to have the head's next equal to me, and now that I have the next guy hooked up already, I'm going to have his prior hooked up to me as well. And there's no return value from free, so I should be good. Okay, so let's see if that's all compiled. Beautiful. No compilation warnings. And let's switch over here again. Let's see if it still builds. We got lucky. So check this out. So before, when we had when we ran it on the short one dash val trace file, we ended up with 70%. This time we're ending up with 80, which is good news, because that means that we're able to reuse some blocks. Okay, that's actually pretty cool. And if we run it with short 2, unfortunately, we can't do a whole lot better, and we can't do any better, in fact, because we're already at 99. Okay, and let's see what else can we do for fun. All right, we can also go ahead and try to GDB this one more time. Okay, and we'll set our breakpoints again. malloc, free, and if we run this with short one trace file, okay, let's continue a couple of times, and if we call print heap, we'll see that. Now I just hit free, so I'm going to hit continue. I'm going to try calling print heap again, and we can see that we now have a free block, an allocated, and a free block, which is actually pretty nifty. And let's see, I'm currently in malloc with size 48, so I should be using this free block. Now remember that I haven't implemented any splitting yet, shame on me, but we hit continue, and we print out print heap. Yes, you can see we allocated that full block. And this isn't going to be a problem for you, right? Because you have the code for splitting right from the slides. Or at least it should be vaguely reusable. Okay, so we're doing pretty good. You know what, let's see how we do with our with the rest of our traces now. Oh, look at that. So we just made it through, count them, right? All 8 traces here. Okay, all the first 8 traces with no errors. The last 2 traces, however, you'll see that the last 2 traces are the realloc traces, and these are the ones that are a real pain in the butt. But we haven't managed to make it through these because, unfortunately, realloc fails the very first time we call it. All right. It would be interesting, actually, to see what happens when we put realloc in here, see how far you can get. Now note that we're not doing any sort of coalescing, again, no sort of splitting, so I don't imagine we'll get very far. But I'm going to go ahead and, through the magic of video editing, paste in some code here. And we're back. So you can see that what I did here was I pasted in some code, and this is actually pretty close to the code that came out of the lecture slides. We went over a generic realloc, and I said that it would be a fine starting point for a realloc because it reuses malloc and free, but it wouldn't get you very far. I've made a few changes. Basically, I'm calling our malloc instead of the regular malloc, and I'm calling our free instead of the regular free. And notice that I've also changed the copy size, initially at least, to be based on the size that I pull out of my block header. So I haven't tested this yet, but it'll be interesting to see how far it gets us. So I save it, and I'm going to do a make, and let me go ahead and run it again. All right, so notice it did not get us a whole lot further. We're still failing on the reallocs, which isn't too surprising for me. But notice that we're failing here at line, let's see, 1708, 65, 65. So we're getting a good ways. If you look at these trace files, though, you'll find that they're actually pretty large trace files. Let me show you. So see, under traces and one of the realloc trace files, you'll notice that sum total we have, whoa, 14,000 lines. We're not getting too far. Okay, but we are getting somewhere. Now we can still use our let's see, we can use our print heap function, which we conveniently have now. And this is something you might want to augment, because it really helps to have a useful and verbose print heap function, just so you can test things. But I'm going to show you how we can use this. So let me run GDB again. Oh, it's already running. So let's go ahead and run it this time using the realloc trace file. Yes, started from the beginning, and I still have breakpoint on malloc and free, I believe. So I'm going to go ahead and continue, say 100 times, and I'm now at free. Okay, and if I want to, just as before, I can call print heap. Okay, and we can see what I'm currently sitting with. Okay. Let's do another 100 calls. Right, and here we go. So let me just have this. And if you notice, oh, see, this is not good news at all. What we end up with here, I've just jumped through a bunch of different lines in my trace, and notice that I have a ton of these free blocks that haven't been coalesced. Okay, so even though I'm continuing to call alloc, the allocated blocks, apparently the allocated calls, and we can actually confirm this. Yes, let us confirm. So if we look at these calls, notice it's very sneaky. All the calls continue to expand the size of the requested block. Okay, and this is why, in my case, whoops, I'm left with all these blocks that are now unusable because I haven't coalesced. So clearly, being able to actually coalesce blocks is going to get you quite a bit further. Okay, and whoops. And again, we are not doing that in our version of realloc, and that is why we're not getting very far. But I think that this should be an uplifting screencast. It didn't take us a long time to get very far. Now we don't have a wonderful utilization, but that's free to fix. Okay, good luck. Thanks for watching.